All right, good morning, everybody. You can all hear me okay?
Yep.
Okay, good. All right. I did put the first lecture online, so it's on YouTube, or you can watch the Confer Zoom version. After today's lecture, I'll upload this one onto YouTube. It does take a little while for the video to upload because these are pretty large files. Because I don't have a very fast internet. Okay. Make sure you read chapter 39 as a reminder. In the syllabus, I lay out, how much you should read before every lecture. You shouldn't read the whole chapter at one time. That's way too much information. I recommend like 2 or 3 sections. But again, go by what the syllabus says. It's typically a couple sections every day to read. And
Professor?
Yes.
So basically, when you read on the syllabus, like it said 6.1 through 6.4, or whatever it was. So that is for the next lecture. So the assigned reading for Monday, we should read for Wednesday's lecture, and then Wednesday's assigned reading should be read for the following Monday's lecture.
Yeah. Actually, ideally, you want to do it a little bit beforehand.
Okay.
I mean, typically, this is what I would do. Before the lecture, I would scan through it. And then after the lecture, I would read through it thoroughly. So when it has the sections to read on that day, those are the sections I plan to cover. And so what you should do is scan through those sections before the lecture. And then after the lecture, read through them thoroughly.
Okay, thank you.
Okay. I just think it's too hard, and this is how I was taught too. It's too hard on the first reading to really get everything. I think it's important that you kind of understand what the instructor is going to talk about, and then read through it thoroughly. Then it'll make more sense, because the book is going to give you more information than I can give in an hour and a half. Okay. The first exam is on September 10th. I'm going to keep you reminding of this, and it will be in person in S102 during your lab time. Okay, and we'll talk about more of this later. Web assignment number 1 is due September 8th, so you get a little bit of time to get it done, but you should get started. Has anybody had trouble getting into WebAssign? Because I've noticed only 21 people have tried it, or actually only 21 people are in the class right now on WebAssign. Okay. Please go ahead and get into WebAssign. I want to make sure you're not having any problems. I've had 1 or 2 students had issues. One of them was my fault because for some reason the assignment was locked, and it should be okay for everybody now. I encourage a couple of things when students take physics. Number 1, and I know this is a COVID, and I know we're in COVID, but you might be able to do this via video, but form study groups somehow. I think it's much harder to learn physics on your own as opposed to when you work in groups. Okay? And like I said, I know it's a little bit harder to do it in this environment because of COVID, but luckily we have technology that'll help us with that. All right? So I encourage that. The other thing is there's a lot of resources online to help you to see the subject described maybe from a different viewpoint. And that might make the light go on in your head in some of these hard topics. So a couple of examples, at least for this topic, on relativity. There's a faculty member at Yale. His name is Shankar. He has a bunch of YouTube lectures. So if you do a search, if you search Shankar, relativity, and Yale, you'll find his lectures on YouTube. Okay, he has like 4 lectures on this topic. I think the last lecture goes a little bit beyond what we're going to cover, but you can look at his lectures. Okay. The other person who moves at a slower pace is Brian Greene. Brian Greene has actually a course. He actually has 2 different courses on relativity, one with math and one without it. Okay. The one without math, though, is an 11-hour video, something like that. So that might be a little bit too long for you. All right. So Brian Greene is a famous physicist / mathematician. I think he's at Columbia. And there's several sets of videos regarding his course on YouTube. Okay. So I think seeing this subject matter from different points of view, I think will help you. Okay. And Khan Academy has a great unit on it too. Okay, great, thanks. So those are some good other additional resources you can use. Okay. Now, lab kits. I was on campus Monday for a couple hours, from like maybe 12 or 12:30 to 2, and I saw very few students coming to pick up lab kits. I mean, not just our class, but just in general. Please pick up your lab kits. Today is the last day where we're going to be handing out lab kits. We need you to pick them up. Okay, just go to Sewell. We're going to be open till 4:30. Okay, so please pick them up. Because starting next week, we're going to start on a regular lab, and you're going to be using some of the equipment in that kit. You're going to need it. Okay. Any questions so far regarding anything?
Is there anything that we need to do for this week's coming lab besides the like lab worksheet that we're doing?
No, yeah. For this, the first lab, it's gonna be kind of a review session on how to analyze data. So I'm gonna give you a worksheet that'll be due the following Friday. But then next Friday we'll start on our lab. You're gonna build something. Okay, you're gonna build some really simple electrical equipment, but then, testing equipment. But you're going to need some of the material from the kit to help you test it. Okay, although it's possible you might have some of these things at home.
Okay, thank you.
Okay. So I see a question in the chat regarding WebAssign. Yeah, in regard to your case, because I saw your question also on a Discord, you probably got to get in touch. You probably got to talk to their support. And I know it's slow to get through. It's a slow process to get through with them. As schools start up, you're going to see their support get slower because more people are going to be contacting them. So the faster you get in touch with them, the better. Okay, so I'm not sure what the issue is with Matt in your case, Matt P. So Matt M, I guess you got help, so that's good. So if you're still having trouble after today, let me know. I used to have yeah, I'm not sure what happened with that multi-term. And I'm sure they have a record. They have a record of your account, so they can take a look at it. Okay. Oh, by the way, thank you for that information. I used to have an inside person that I used to contact, but that person left. So did our representative. Our representative left, and so it's become much harder to get in touch with them. But if use that number and name that you see in the chat, okay? Use the name and number that you see in the chat to contact WebAssign. That'll help. Okay. All right. Any other questions? All right, so
Yes.
I'm sorry.
verify something real quick? So if our labs are at 11 on Fridays, then that's when we're going to be taking our exams.
Yeah, I reserved 5 of those days to give you the exams.
Okay, I just wanted to make sure because for some reason I thought it was at 9:30, like no matter what, but it depends on our lab time then.
Yeah. So what I
Okay.
did, I scheduled the lab times right after each other. So as one group goes out, the other one comes in to take the exam.
Okay.
So yeah, there's only going to be 16 people in the room to take the exam, which is nice. It'll be spread out. So we'll still be socially distanced. We'll have to wear a mask. So anyway, and it'll be in a fairly large room, in a room that sits over 40 students. So yeah, there's only really three of the 8 meetings where we're actually going to talk about the lab. But remember that I'm signed up to be there 3 hours for each one of the labs. So 1.5 hours is for the exam. The other 1.5 hours, is an open lab time where I'm available to answer your questions. So my open lab time is listed on Canvas. So I think for the 9:30 group, the open lab time is before the exam. However, you can come anytime I have open lab time, doesn't matter. And you can ask me questions on the lab. Okay, especially the lab kits. You know, it's hard to do the labs at home. You can come see me and I can help you. I can help you make things work. So Matt, a question regarding the lab time. So when you signed up for 210L, on the schedule it tells you what your lab time is. Okay? So on 8 of those lab times you will come in person. So on September 10th, you'll either come at 9:30 or 11, whichever lab time you signed up for. And I will give you the exam at that time. The other 1.5 hours, I'm there for open lab. Does that make sense, Matt? Okay, so and I can talk about it more on Friday. So on Friday, this Friday, those of you who signed up for the 9:30 lab, I will be lecturing about the worksheet at 9:30, and then I'll do the same thing at 11 o'clock. Okay, for the other group. All right, so on Friday, I'm going to see half of you at 9:30 and the other half at 11, based on when you signed up for lab. And you can tell by going on Canvas and seeing the lab section you're in. Okay. Just look at your Canvas 210L shell. It'll tell you what time you're going to have your lab meeting. Yeah, on Friday, this Friday, it will be on Zoom. And then the following Friday, it will also be on Zoom. But on September 10th, it'll be in person. Does that make sense? All right, this Friday via Zoom. Okay. So, my objectives today are to talk about length contraction, do some examples, talk about simultaneity and synchronization. Okay, and again, we'll talk more about the lab and how we're going to run it on Friday. Just show up for the Zoom session on Friday. Okay. So, the other day, we talked about time dilation. I kind of changed a couple of things in my notes, just some of the wording. Basically, time dilation says that moving clocks run slow, and I made a mistake. I still have a mistake there, but moving clocks run slow. So, in other words, we looked at 2 cases. And I'm going to use this example a lot. And this board is hard to erase. I said, if you do an experiment where you have a person standing on a rocket ship, they send a beam of light towards a mirror, and then the mirror reflects it back. If this distance is d, then the total time that they measure is 2d over c. Okay? Now, this is the prime frame. We're always going to say the frame moving relative to us is the prime frame. Okay? Now, if we observe this process as the rocket goes by, we don't measure the same time because the light takes this path. And so we measure a time, and I'll go back on the slide. We measure a time delta t equals 2d over c. I'm sorry? Someone's got a lot of feedback. All right. 2d over c times gamma.
I think it might have frozen up again, Professor, your screen.
I froze up again? All right, thank you. All right, I don't know why it only happens in the morning. Okay, I gotta restart the video. You okay now?
Yep.
Okay, so my problem then is I'm gonna have to take my 2 videos I created at home and join them. Okay, so I apologize. I don't know, it's for some reason in the morning I'm having trouble. If I keep having trouble, I'm gonna start going to campus and doing the lectures. Okay. All right, so what I had said was that when we do this experiment, or when somebody in the rocket does the experiment, they measure this as the time it takes for the light to go to the mirror and back. But if we see the rocket go by us, we're going to measure this time 2d over c times gamma, where gamma is 1 over the, let me rewrite this. Gamma is 1 over 1 minus b squared over c squared, square root. And gamma is bigger than or equal to 1. And so we measure a greater time interval between those 2 events. So we say that the moving clocks run slower. We say that the rate at which the clocks tick in the moving frame, the rocket, is slower. Meaning that person ages slower than us. Okay? Any questions? And it's a bizarre thing.
How about astronauts in like the International Space Station? Are they going fast enough to where there's like a real difference?
But it's very small.
Yeah.
It's a small difference. So really it becomes significant when you're going close to the speed of light. They're not, the speed of light is 300 million meters per second. That's fast.
Yeah, that might tear apart their space station, I think.
So question, do they physically age slower? The answer is yes. Okay, so I'm going to provide to you some experimental evidence for that. Okay, and that's the one thing people have a hard time believing. They say, well, it's it's just an idea, but it's true that we haven't done this experiment on a human being over a long period of time, but we've done it over very short periods of time. Okay, or in physical, you can actually observe it with physical systems. So I'm going to show you an example of this on a physical system. Okay, and people have a hard time believing this. Because remember, this represents what you would physically measure. Okay. Now, another thing we talked about the other day was the idea of proper time. When you're measuring proper time, what you're doing is measuring two events at the same location. Now let's look at another thing. Let's imagine this rocket goes by us. So let me draw another picture of this rocket. And at this location, the light wave is sent. And I'm going to mark it as Y1. Then at this location, the signal is received by the person on the spaceship. And so I'm going to mark that as Y2. Okay, and I can measure that distance. I can call it L0. Okay, and I measure that distance. Now, how do you measure distances? Well, you have to locate the endpoints at the same time to measure distance. So how big is this distance to me? Well, to me, that distance, L0, is going to be the velocity of the spaceship times the time it takes for the signal to hit the mirror and come back. I'm sorry, for the signal to go to the mirror and come back. Okay? Delta T is the time it takes for this event to occur as measured according to us. So that's what I call it, the distance between those 2 points. Well, what does the person on the rocket observe? What does the person on the rocket measure? Well, first of all, I can measure these 2 locations at the same time, but the rocket can't. So there's going to be a problem with that. Okay. Well, if this is my time interval between the 2 events, what is the time interval between the 2 events according to the rocket? Well, it's this. So the rocket is going to say the distance between those 2 points is going to be V times delta T over gamma. Which is going to be L0 over gamma. Gamma is bigger than 1. So that means that the rocket, the person in the rocket is going to say, this distance is shorter compared to what I measure, compared to what we measure. So distances are contracted. So if you have a meter stick that zooms by you and you use your meter stick to measure the length of that thing that zooms by you, you will measure a value that is shorter than yours. Objects that move by you are length contracted. Okay? Again, another weird thing regarding relativity.
So L naught that is what's measured by an outside observer watching the rocket go by. Do I have that correct?
Yes.
Okay.
Yeah, so this is us. We're stationary relative to these 2 points.
Okay.
And we can measure the separation between these 2 points. We can locate those 2 endpoints at the same time so we can make that measurement. We call it the proper length.
Okay. Thank you.
So this idea the idea of length contraction came from Einstein, but this equation had been in existence already because Lorenz had used this idea to explain the fact that the result of the Michelson-Morley experiment, that they got no result. So this is called Lorenz contraction because this idea did exist, but it was used in the wrong manner. And in fact, the explanation that Lorenz and Fitzgerald used to explain the Michelson-Morley experiment really was disproved later on by Thorndike and Kennedy. Okay. So I want to give you an example where time dilation takes place. An experiment was carried out in 1941 by a person named Rossi that illustrated time dilation. And then there was another version of it in the 60s done for educational purposes. And this experiment involves some weird particles called muons. They're exotic particles. Muons are unstable. In fact, muons come from another particle that's unstable, called a pion. They come from cosmic radiation. They're produced because of cosmic radiation. And then the pions are produced in the atmosphere, way high in the atmosphere. They decay into muons. Now, what does it mean when something decays? Well, they break up into other particles. So the muon, denoted by the letter mu, will decay into an electron and 2 other particles. The muon will do this. If this is positive, there's different versions of positively charged. You get the electron that's positively charged, the antiparticle, it's called the positron, plus 2 other massless particles called neutrinos. Don't worry about this stuff, okay? So it disappears. It essentially becomes something else. Okay? So these particles are way high in our atmosphere, and they come down towards the Earth. And we can detect them. And they decay in the following manner. Their decay is governed by this equation. The number you have at any time is equal to the number you started with times e to the minus t over tau, where tau is the lifetime. And it's 2 microseconds. Okay? Basically, the lifetime is how long expires until this ratio is 1. Okay? So that's 2 microseconds. And naught is what you started with, n is what you have after some elapsed period of time. So, and I'm going to use, I'm not going to go through the exact experiment, but I'm going to use an example that gets you to understand the experiment.
Is that E like the natural log E 2.71?
Yes.
Okay.
If you've had chemistry and you've talked about nuclear decay, it's the same equation. I don't know how many folks have had chemistry. I don't know if you do it in biology either. I'm not sure. So let's say these particles are produced 9,000 meters above the Earth. So let's say, imagine muons are produced okay, and again, I'm not going to give you the exact values of I'm not going to tell you the exact experimental nature, but I'm going to give you the idea of the results. So let's say there's 10 to the 8th muons in some region at this height. Okay. And we know we have an idea how fast they move. Let's say they move at 0.998 times the speed of light. Why did I choose that number? Okay. Well, I run it's really not exactly the number. I chose that number because it's going to make gamma a nice value. So this implies that gamma is 1 over the square root of 1 minus 0.998 c over c squared. Notice when I write gamma out, I don't put the actual value of c, I say 0.998 c, so the c's cancel. This is about 15. So how long does it take for a muon to get from 9,000 meters to the surface of the Earth? Now, granted, the experimental details are more complicated than what I'm discussing here, but again, I'm just giving you the general idea, okay? So what is the amount of time it takes for the muon to get from 9,000 meters to the surface of the Earth? Well, the speed is, remember, c is 3 times 10 to the 8th meters per second. If you do this calculation, this number is about 30 microseconds, 30 times 10 to the minus 6 seconds. So if I have this many muons at 9,000 meters above the surface of the Earth, how many do I have when they get to the Earth? Okay, that's the question. I just use this equation. So I said, the number I have when this amount of time has elapsed is 10 to the 8th times e to the minus 30 microseconds over 2 microseconds, because that's the lifetime. That's 10 to the 8th e to the minus 15, sorry. And that's approximately about 30. So what that says is, if I have this many muons this far above the surface of the Earth coming towards the Earth, when they reach the Earth, this is how many I'm going to have left, because in this time they decay. These things fall apart. I don't have muons anymore. I have positrons and some other stuff. That's what the theory says. But guess what? Guess how many I detect? Well, I don't detect this many. In fact, I detect way more. The number I detect is approximately is approximately 3.7 times 10 to the 7 muons. Like, wait a minute. That's over 1 million. My error is off, is like a factor of 1 million. What's the deal here? Theory says 30. I would detect that many. In fact, that's what the experiment. In the experiment, they measured way more than they expected. Why is that? Why am I so far off? Well, this 30 microseconds is measured in our frame. The lifetime of 2 microseconds is in the frame of the muon. If 30 microseconds elapsed for us, how many microseconds elapsed in the frame of the muon, the rocket? Imagine, the muon is the rocket, okay, in the example. The muon is in the prime frame. So if delta t is gamma delta t prime, then delta t prime is delta t over gamma, which is going to be 30 microseconds over 15. So according to the muon measures that only 2 microseconds have elapsed. And so accordingly then, what should be measured is the following. That's the reason why it's because of relativity, because of time dilation. So you have a physical system now that shows that time dilation exists. Now, do we observe these kind of things with human beings? There was an experiment that was carried out, I think it was in the 70s. Of course, we can't move that fast. We can't move at those kind of speeds. They had an airplane fly around the world for 24 hours. Okay, so their airplane fly for 24 hours. And they wanted to look at time dilation. So what they did was they put an atomic clock, cesium clock, on the plane and one on Earth. And they, when the plane took off, they started. Now, there's one issue with this experiment that is that not only does this experiment involve special relativity, it does involve general relativity, because the airplane doesn't go in at constant speed. The airplane has to accelerate. And so they did calculations taking into account special and general relativity. So the calculation is more complicated than what we have here. So the plane flies 24 hours and lands. And so what they then do is compare the clocks. Now, don't expect a big time difference because, number one, the plane's only going 500 miles per hour. It's nothing compared to 300 millimeters per second, okay? So, but there was a time difference that agreed with theory. It's about 90 nanoseconds. Okay, so the airplane's clock was slower by about 90 nanoseconds. And the precision of the clocks is better than the 90 nanoseconds. Okay? So there's a couple of experiments that shows that that this time dilation is real. Now, it hasn't been applied to human beings for over a long period of time, because basically what we need to do is send someone in a spaceship for like 70 years at a fairly high speed. Then you can see the effect on a human being. But I think even at the speeds we can achieve now, it's not going to be a big difference. It's when you get to about 10% the speed of light, then you can see the effects more clearly. Okay. Questions about this example? So one more thing too. If the distance from the location where the muons exist to the Earth is 9,000 meters, and the muons are going at such a high speed, the muons are not going to say that distance is 9,000 meters. The muons are going to say this. The muons are going to say it only traveled 600 meters. Because that distance is contracted to them. That's why they live only 2 microseconds, not 30. Right? Only 2 microseconds have elapsed for them, not 30. Because that distance is contracted. Okay? So there's one example. There are other examples where you can show the ideas of relativity working, but it has to do with energy. We're going to talk about E equals mc squared. You can directly measure that effect in the laboratory with exotic particles. Okay. So let's do a simple example involving these equations. So astronauts in a spaceship, they're traveling at 0.6 c past the Earth. And they sign off from space control saying that they're going to take a nap for an hour. And they'll call back in an hour. How long does their nap last as measured on Earth? Okay, so you have these astronauts in a spaceship. We're given V is 0.6 c. We're the stationary folks. The spaceship is moving past us. They're the moving frame. So 1 hour is delta t prime. And we want to know how long is that according to us on Earth. So we use the equation delta t equals gamma delta t prime. Well, what's gamma? And again, I'm writing gamma this way in terms of c, because then I can just cancel the c's. I don't want to write 0.6 times 3 times 10 to the 8th and then divide by 3 times 10 to the 8th. That's a lot of writing for me. It's easier to do it this way. So 0.6 squared is 0.36. 1 minus 0.36 is 0.64. The square root of 0.64 is 0.8. 0.8 is 4/5. And 1 over 4/5 is 5/4. So then the elapsed time okay, our clocks run faster. No, I will say that the effect is real, but the time there, the speed is kind of unrealistic because we're not at the point where we can make human beings go that fast. Okay. Questions? All right. So there's two people of the same height. They pass each other in different elevators. Let's say one elevator is going down, the other one's going up. According to relativity, what do they conclude about each other's heights? What would you say?
You said one elevator is going down, one elevator is going up.
Yes.
They would say that they're the same height but shorter. If they're going equal speeds,
In opposite directions.
opposite directions.
So let's say I'm
Oh, okay.
I'm 6 feet tall and I observe the person going by me. What am I going to say about the person going by me? Is that person
if
gonna be
you're
short?
going fast enough, you're going to say that they're shorter, right?
Yes. In fact, both people are going to say that they're shorter than the other person. And they're both correct because that's what they measure. Yeah, so they're going to look, each person is going to say the other person looks shorter because that's what they would measure. That's what's weird about relativity. Okay. So now I'm going to talk about, and this will probably be maybe the last thing I talk about today, we'll see. I think it's a difficult topic, so I actually sent you an email with a different example. Because of this topic, some more examples, the better. And notice I'm not doing a lot of complicated math. It's the logic that's complicated. Okay, that's the one thing that's difficult about relativity. It's the logic that's complicated. So here's the thing, two events that are simultaneous in one reference frame, it turns out they are not simultaneous in another reference frame. In other words, because of Einstein's two postulates, because of relativity, simultaneity is not absolute. The question is why? And really because of the fact that the speed of light is constant in all reference frames. And to understand that, we got to talk about how we can synchronize clocks. And there's a lot of ways of synchronizing clocks. Okay. And so I'm going to talk about one of the ways of synchronizing clocks. This is something that Einstein used to understand relativity. And this example might be a little bit complicated. That's why I sent you an example of another example, which I think is a little bit easier. But I do want to show you Einstein's example. And there's a lot of different kind of physical arguments and thought experiments you can do to understand this. A lot of times books and faculty don't spend time on this, but I think it's important, even though it's kind of hard. And I will say the homework problems on this topic are not going to be as hard as what I'm going to go through right now. Okay. All right. So how do we synchronize clocks? Well, suppose we have two events. Okay. Let's say I do the following. I have a person standing in the middle, okay, halfway between the two ends of a railroad car. If I send a light here in this direction and a light here in this direction, so that they reach the observer at the same time, then I would say that the clocks are synchronized. Furthermore, if I'm standing in the middle, if I want to synchronize this clock and this clock, I just send a signal in both directions because I'm halfway in the middle. I'm assuming the speed of light travels the same in all directions. That's an assumption that hasn't been proven yet. Okay, but let's say I stand in the middle of a railroad car and I send a light signal towards the two clocks on the ends. If I'm exactly in the middle, both clocks are going to receive the signal at the same time. The clocks are synchronized because the events will be simultaneous. That's a way you can synchronize clocks. There's other ways. In fact, the example textbook that I gave you called by R.A. Mold gives you, it's on Google Books, gives you another example of how to synchronize clocks. It's about a page of reading if you want to look at it. Okay, it's in chapter 2 of that book. I would only read chapter 2 of that book. Okay. Okay. Here's Einstein's example. Imagine there's a railroad car going by a platform. Let's pretend we are the observers on the platform. Okay? So let me draw it real quickly. Here's a platform. And we're halfway in between. This is us. Okay, this railroad car is going to the right at speed v. And there's an observer, somebody else, on the car. And I'm going to call this B prime and F prime. So this railroad car goes by us, and at some instant in time, lightning strikes the front end and the back end of the railroad car. So lightning strikes here and here. So, and it leaves a mark on the railroad car and at point B and point F. So there's a mark here and here to indicate that separation. Okay? And this happens as that railroad car is going by us. And I can measure this distance. You and I can measure this distance. Okay? We see the two events occur at the same time. But what about the person on the railroad car? Yeah, they would see it at different times because as the light is coming towards the observer, the observing is moving towards the light. Same thing here. Now here, as this person moves to the right, this light is trying to catch up to the person. Because remember, the light speed is always going to be 3 times 10 to the 8th. And so what's going to happen is this person is going to see the lightning strike at the front occur before the lightning strike at the back. So in that person's frame, the events are not simultaneous. Okay? We say they happen, we say that the lightning strike here and here happened at the same time, but that person says no. Lightning struck the front end first and then the back end. Okay. So what we need to do is calculate, we need to calculate the time difference between when the lightning strikes the front and the back. We need to calculate I'm going to call it delta t times b prime f prime. That's the time difference this person observes between those two events. In order for me to do that, I need to do this. I need to calculate t sub b prime, or t sub f prime, and t sub b prime, which is the time it takes for the beam of light to go from the front end of the train to the observer. I need to calculate the amount of time it takes for the light from the back end of the train to reach this observer. So I need to calculate both. I take the difference and I have my value. Okay? So instead of redrawing the picture, because it's going to take time, I have this slide, which I drew out the picture. And so our goal is to calculate T sub f. Now, observer O again says that the distance between the marks B and F is L naught. Is that distance the length of the train?
No.
No, because that train, when we see that train go by us, that train's length is contracted according to us. So really the length of the train is actually longer than that. But we observe that the distance between the two strikes is L naught, BF, okay? We know that this train is longer than this distance because this thing is moving. All right. I want to calculate T sub f prime, the time it takes for the wave to go from here to the observer. Okay. In that time, in time TF, sorry. The train, or actually O prime, moves a distance v times t f prime to the right. And in fact, if I call this the origin, right? If this is the origin, isn't it true that I can say the position of O prime is V times T, because what happens is as O prime goes this way, its position relative to where it started increases by this amount. And so when the light from the front reaches O prime, XO prime equals V times T sub F prime. But what about the position of the wave front for the beam of light? The beam of light starts here and then moves towards O prime. it starts at this location, which is measured with respect to this person. Okay? So it's going to be half this length. So the beam of light starts at L B prime F prime over 2, because it's not L naught, because in reality this person measured a much longer length, minus C times T. And when light from front reaches O prime, then we can say X beam equals L B prime F prime over 2 minus C times TF prime. But when that's the case, the position of the beam of light equals the position of O prime. So I set them equal to each other. And solve for TF prime. Okay, if you do that, you get the following. I'm going to skip the algebra. What you'll do is you'll get TF prime over C plus V. That's how much time it takes for the lightning bolt, the light from the lightning strike to reach O prime. Now we can do the same thing for the back of the train. Okay, so let me show you a blown up picture of the back of the train. And again, what we want to do is calculate T sub B prime when the position of O prime matches the position of the wavefront of the light beam. But this equation is going to be a little bit different, because in this particular case, the beam of light is moving to the right.
Professor, I think your thing froze again. We can't see you.
Again?
Yeah.
Oh, okay, hold on. Jeez, sorry. I don't know why. All right. Yes, I'm showing that slide. Okay. All right, good. Sorry about that. It's unusual this semester. I'm having that kind of this much trouble. Okay. Thank you. So this is the back. So this is the case where the light strikes the back of the train, and like I was saying before, we need to solve for the time T sub B prime when the position of the observer matches the position of the wavefront coming from the back of the train. So the logic is the same. The only difference is the following. The position of O prime is the same. So we want to calculate this. We just got to change these letters. When light goes from the front end, when they match, you get this. The problem is with the other equation, okay, with the beam of light. The beam of light, if this is the origin, this location is minus L B prime F prime over 2. So I got to change this to a minus sign, and I got to change this to a plus sign because the light wave is traveling to the right in a positive x direction. Okay, so in that particular case, I end up setting these two equations equal to each other. And I get now if I do the algebra, I'll leave that up to you. You get t sub b prime, if you do the algebra, ends up being L prime, b prime f prime over c minus v.
Professor,
Yes.
is there a 2 in the denominator or no? Is it 2 times c minus v?
You know what? You're right. There's a mistake in both equations, isn't there? Let me check my notes real quick. Yes, you're correct. My notes, my PowerPoint notes have a mistake. Thank you. I guess I should have just done the algebra. Okay, so what I want to calculate then is I want to calculate it. That gives me the delay time. Okay? And this is where the 2's will cancel out. And what do I get? I'm going to get oops, made a mistake. Okay, so this is delta t b prime f prime. Now, I want to show you something about gamma. Let's look at gamma squared. Let's multiply numerator and denominator by c. Or c squared, sorry. Okay. So gamma squared over c squared is 1 minus v squared over c squared. Okay. So delta t b prime f prime is equal to v gamma squared L b prime f prime over c squared. Okay, so this person on a train says this is the time difference. But L B prime F prime is equal to L naught over gamma. The distance between B and F is contracted. And so we can write the following. One more thing. This time is measured in whose frame? This time difference is measured in whose frame?
For the observer on the train?
Yeah, by the person in the train. Okay? This person wants to know how far off the other person's clocks are. So what do? The train is moving relative to him, right? So I got to divide that by gamma. So then the time difference is V L naught over C squared. So the person on the train says, our clocks are off by this much. That's what the person on the train says. The person on the train says, our clocks are off by that much. And in fact, the person on the train says, the clock in the front, let me rephrase that. The clock at F prime, or at F, is ahead of the clock at B because the light wave came to me first from F than from B. It turns out that if two synchronized clocks move by you, they're always going to be off. According to you, you're going to say that those clocks are off by this amount. With the trailing clock leading. Notice in our example that to O prime, the trailing clock is F, the one at F. Because if the train moves to the right, then according to O prime, the platform is moving to the left. And so F is the trailing clock. Okay, so when two synchronized clocks move by you, the trailing clock leads by V L naught over C squared.
Just to confirm that L naught is the proper length of the car as measured by O prime and not the observer?
It's measured by the platform.
Okay.
Yeah. Okay? So I have this described from a different point of view in your notes. Okay? And then I also sent you an email giving a completely different example. So no matter how you look at it, you're going to get the same time difference. So I'm going to finish off today with an example. I might go a couple of minutes. If you need to leave, go ahead and leave. I want to... actually, you know what? I'm not going to do this. Actually, I'm not going to do this example because I can't go. I have a meeting at 11. So I'm actually going to stop here because this example will take like 5 minutes. So, or maybe 10 minutes. So this example that I have here will help to illustrate what I've been talking about. And you'll notice in my discussion now and through Monday, I'm going to be going through using the same example over and over again for different, in different contexts. So hopefully that's going to help you to better understand the material. Please read the document I emailed you, especially now that we've covered this topic, and I'm hoping that's going to help to clarify this. I know this is hard to this is a topic that's hard to swallow. I understand that. I think though, as we get more to the formal way of describing things, it'll get a little bit easier for you. Okay? Questions?
Do you have this example? Did you go over it in one of your YouTube videos? Like, can we find it?
This example, it'll be in this video because this will go on YouTube. If you look at my videos from last semester, I have this example.
Okay, thank you.
And this is a fairly new example. That's why I still have a couple of mistakes in the notes. Okay. And by the way, thank you for pointing out my mistakes. I'll fix them. And I'll give you a new copy. All right, so we'll see you on Friday. I'll see some of you at 9:30 and some of you at 11 via Zoom.
I have a question real quick.
Sure.
Do you have a copy of the PowerPoints anywhere? I didn't look that hard.
I emailed them to you several days ago.
Gotcha. Yeah, and then I'll find it. Okay, thank you.
Okay. If you don't find them, I can email them again. I don't put them on Canvas just because of issues with making them accessible and things like that. So it's an extraordinary amount of work to actually redo those notes. And yeah, if you there's a Discord on Canvas, so please use it. Please sign up and use it. Okay. It's on the Discord invitations on Canvas. All right, I'll see you guys on Friday.